Before we run off and start building lump circuit abstractions, it is worthwhile at this point to spend a few minutes thinking about what assumptions we really have to make in order to create these lump circuits. So recall we took these lumped elements and modeled them by their VI relation. We defined a V and an I for each element. In general, we just cannot go around doing that. Okay, that seems like a huge simplification, and in general, that is not true. So it turns out that we have to make some pretty substantial assumptions in order to make that true, and I'd like to spend this next segment to discuss that. So for a light bulb filament example, for instance, we defined a VI relation for that, and we need to understand under what conditions is that true. Now, in general, for circuits that we will build in this course, we won't argue during each of those building experiments whether the assumptions are true or not, but it's really worthwhile for us to spend some time right at the beginning of this course to make sure that at least this first time our abstraction is reasonable. And then for future times, we will simply assume that is true. So in this case, ensuring that the abstraction is reasonable is tantamount to making sure that the V and I that we have defined for the element are valid. There's a V here and an I here that we've defined for the element, and I need to be sure that those two are truly defined in a unique manner for the element. So let me start with looking at the same filament and look at under what conditions I might be defined. Let me do a quick segue into one other a quick thought that came to my mind, which is as you progress through the rest of 6002, you really won't need a lot of this material that we will cover in the next few minutes to understand what must really be true for us to make this lump circuit abstraction. However, many years later, as engineers, when you build systems, you might happen upon some circuit or some element which may not quite behave the way you think it should be. And it could well be that the material in this segment might come to your rescue and explain exactly why it is that the circuit is not behaving like you want it to. All right. So going back to our light bulb, I'm going to look at what kinds of assumptions we have to make in order for the current I to be uniquely defined. So let me just call this area here, the surface here, SA, and call this SB. And so I will be uniquely defined if the I going into SA is equal to the I, equal to the current coming out of SA. Out of SB, I'm sorry. Okay, so let's say if I have some current going into SA here, then I will be uniquely defined if the current coming out of SB is the same as the current going into SA. Okay, so let's take a look at what must be true for that to happen. So I'm going to start by putting a little black box around this filament so I can look at the total amount of current coming in and apply Maxwell's equations to figure out under what conditions I going in equals the I coming out. So recall I have built this little box for myself around the light bulb, and I'm going to call the current going in IA and the current coming out IB. And SA is the A surface and SB is the B surface of my filament. Now, I also know that IA is given by integral over SA J dot ds, and IB is given integral over SB J dot ds, where J is the current density, and I've just integrated over the SA and SB surfaces to get the current. So as I said earlier, my current I is uniquely defined if I can show that IA equals IB. In that case, my current I will be uniquely defined. So let me give you the result, and then I'll show you how to derive it. I will be uniquely defined for the element only if dq by dt is 0 for the filament. Del Q by del T here is the rate of change of charge, where the charge Q is the charge inside the box here. Okay, so I claim that make the claim initially that the current is uniquely defined only if del Q by del T equals 0 for the filament. So how do we get that? So from Maxwell's equation, we know that integral SA J dot ds for the current going in minus the integral over SB J dot ds equals del Q by del T. So what I've simply written here is one of Maxwell's equations, which says that the total amount of current going into some closed surface is related to the rate of change of charge within that surface. So if you look at within the volume contained by the surface. So in this case, it is integral j dot ds over SA minus integral j dot ds over SB equals del Q by del T. So this component here is IA, and this component here is IB. Now, IA will equal IB only if del Q by del T equals 0. Okay, so IA will equal IB only if del Q by del T is 0, but in general, del Q by del T doesn't have to be 0. Okay, there's no reason why for some component that I pick up that the del Q by del T is going to be 0. Yeah, I have no way of knowing that. So, so does this mean that we are in trouble? Okay, so are we stuck? We seem to be stuck because I wanted to show that I was defined for the element, and for I to be defined, IA must equal IB because the current going in must equal current going out. But I've just shown that the difference of these currents, IA minus IB, is del Q by del T, but that doesn't have to be 0 in general. Okay, so it looks like we are in deep trouble. So what do we do here? So I'm going to pause for a few seconds while I give you some time to think about what might be a trick that you can use. Okay, this might be one of the most powerful tricks that we have made in our EECS field that has enabled us to build really, really interesting systems in a really simple manner.